Hello. What I would like to do today is I would like to use the power of making free body diagrams to help us solve problems using Newton's second law. So to begin, we're pushing horizontally on a refrigerator. You're pushing with a 220 Newton force. The fridge is sliding across the floor with a 200 Newton frictional force between the floor and the fridge. The fridge has a mass of 50 kilograms, and we want to find the acceleration of this refrigerator. So to get us started, I've already made an interaction diagram. You can see that the system I'm choosing is the refrigerator. There is a gravitational force on it from the entire Earth. The floor is squished by the fridge, so the floor is pushing back up with a normal force on the fridge. There is a frictional force, as it's written in the problem, between the refrigerator and the floor, and you are pushing it. There are other forces drawn on there, like with you interacting with other things, but let's just focus on the fridge right now. So I'm going to make a free body diagram for the refrigerator. I know that there are four forces involved because I can count them here. There's a gravitational force, normal force, frictional force, and a push. Let's assume that the floor is a level, horizontal, flat floor. So if I draw my forces, then I'm just going to quickly make some axes here. If I draw my forces on the refrigerator, I know that there is a gravitational force straight down towards the center of the Earth, gravitational force by the entire Earth on the fridge. I think we have enough experience now. I don't need to write out that whole thing, so I'm just going to label that as gravitational force. We know that this is a free body diagram for the fridge, so we know that that's acting on the fridge. I've also got a push. Now, I didn't say you're pushing left, you're pushing right, but we can imagine this however we want. In our minds, we can think of this refrigerator as being pushed to the right, since most of us find that to be the most comfortable way of thinking about it. So I'm going to draw an arrow to the right. F, let's say that's the push by you on the refrigerator. Not going to add that onto my notation there, but we know we have the experience to know, excuse me, that that's the push by you on the refrigerator. Those are not equal amounts. In fact, I know that this one is 220 newtons. The gravitational force, 50 kilograms times 9.8 newtons for each kilogram. I know that that number is going to be 490 newtons. I know that there is a frictional force from the floor on the refrigerator, and that's going to be opposite the direction of motion. So if I'm sliding it to the right, that frictional force is going to be back to the left because frictional forces are always going to act opposite the direction of relative motion. So if the fridge is sliding right across the floor, then the frictional force is back to the left, and that's 200 newtons. Wrote that pretty tiny, but that's 200 newtons. So those are unequal amounts left and right. I've got 220 to the right, 200 to the left. And then we've got a normal force. Now, my normal force, since the floor is flat, the normal force is going to be straight up. And I also know that there is not going to be any motion like along a vertical axis. There's going to be no up or down motion. And so I know that the velocity, vertically speaking, is not going to change. So vertically speaking, those forces are going to have to be balanced. The gravitational and normal forces are going to be balanced because they're the only two that act vertically, and we know there's going to be no change in velocity vertically because there's no motion at all vertically, unless we really change the story, like you throw the refrigerator for who knows why you would want to do that. So I know that the normal force is also 490 newtons because by Newton's first law, these have to be balanced since there's no acceleration vertically, constant velocity of zero vertically. So there is my free body diagram. I also want to stop and think for a moment about direction, like signs, positive, negative. So I'm going to say that the positive direction, and this is mine to choose, I'm going to go with what most of you are usually comfortable with. So I'm going to say that to the right is the positive direction. Vertically, I don't really need to assign a positive direction, although most of the time, most of my students find thinking about up being positive as a simpler thing, although that's not going to be relevant for this situation because the forces are balanced vertically. But we've got a positive direction to the right, so this push to the right is going to be a positive force, and this frictional force to the left is going to be a negative force, because remember that we always want to pay attention to direction when we're thinking about forces, because force is a vector. So I can use this diagram to know that the net force, sigma F, the sum of all the forces, the net force is the total. Well, these two add up to 0. I don't care about those. I'm just interested in the horizontal. So I've got a positive push and I've got a negative frictional force. Now you might be thinking, wait a minute, I thought we were finding a sum, we're finding a total, and you wrote subtraction there, F push minus frictional force. And yeah, you're right. I'm adding together a positive force and a negative force. So I've got positive 220 newtons here plus negative 200 newtons there. And it's just as simple as taking the amount to the right minus the amount to the left, because adding a negative number is the same as subtracting the amount. So I could think of this as a positive F push plus a negative F friction, and that gets me to the same result as just choosing to subtract those two. So yes, I am finding a total, and I'm finding a total by subtracting those because one of them's positive, one of them's negative. So there's that. And when I do it that way, then sometimes I could also end up, like if this one were smaller than that one, then I could end up with a negative net force, and that would be fine. That would just be telling me that my net force is in the opposite direction of the way that I said is positive. So now that I've got a net force, now I'm ready to use Newton's second law. And I'm sure somebody watching this is thinking, why didn't he just substitute in those numbers, 220 newtons, 200 newtons, and come up with a number? We will, I will, you will. I just like to save that a little bit later until the end, but we'll do that. So Newton's second law, the net force is equal to mass of the fridge. The fridge is our system. So the net force on the fridge is equal to the mass of the fridge times the acceleration of the fridge. So now I can use what I figured out from the free body diagram to make a substitution into that left side of the equation. So I'm going to substitute into the left side of the equation that push minus the frictional force, and that's equal to the mass of the fridge times the acceleration of the fridge. And I know a whole lot of numbers here. I know that the push is 220 newtons. I know that the frictional force is 200 newtons. I know that the mass of the fridge is 50 kilograms times the acceleration of the fridge. So the acceleration of the fridge is the only unknown here. So this is definitely something I can solve. 220 minus 200 gives me 20 newtons as our net force. So my net force of 20 newtons is equal to 50 kilograms times the acceleration of the fridge. Now to solve for the acceleration of the fridge, then I just need to divide both sides by the 50 kilograms. So the acceleration of the fridge is 20 newtons divided by 50 kilograms. And 20 newtons divided by 50 kilograms, the number 20 divided by 50 is 2/5 or 0.4. And that is a positive number, by the way, because I had a positive net force I get a positive acceleration, which tells me that the acceleration is in the positive direction, so it's accelerating to the right. So there's an acceleration of positive 0.4 is the number, and the unit, newtons divided by kilograms, gives me a unit for the acceleration of meters per second, or 0.4 meters per second for every 1 second that that refrigerator is being pushed. And I know that the acceleration is in meters over seconds, meters per second each second, because when I'm using newtons and kilograms as my units of force and mass, then the unit that goes along with those is meters per second per second. These three units, newtons, kilograms, and meters per second squared, are units that fit together to make Newton's second law. This way, instead of having some other constant besides just the mass here, like if we had a different set of units, if we had a different definition for how much force is 1 Newton, then we would have a different number in here, but we don't. We defined 1 Newton to be exactly the amount that 1 Newton of force would be the force that would give 1 kilogram an acceleration of 1 meter per second per second. So based on our definition of those units, when we have newtons here, kilograms here, we're going to get meters per second squared there. So thank you very much, and I hope you enjoyed that immensely, and I'll see you soon.